So this one is QAM. So this one is, to be specific, this one is 4 QAM, not the 16 QAM. So at the end I'll tell you the difference between 4 QAM and 16 QAM. So there's some minor differences between these two. So starting with the general commands that we use, obviously CLC, clear all and close all. So after that, m is equals to 4. So m is equals to 4 tells that each word of that message signal that we are sending is 4 bits long. Now what I've done over here is I've printed many variables. So just to explain the code, I've printed many variables. See m, x, w over here and map over here and few more variables down here, but you need not do this. I just did it to explain the code. You can do it for your understanding, but it's not required. Now m is equals to 4, x is equals to 0 to m minus 1, which will give you again 4 values. These are the 4 values that you're going to send. Each value is 4 bits long. These are words which are 4 bit long. Now w is equals to quadrature modulation of x comma m. Over here, what is x? So it is the inbuilt function of MATLAB which does the quadrature modulation for you. You need not write the code for it. So it makes your life easier. Now x comma m, where x is the message signal and m is the alphabet size. Obviously told you m is the alphabet size, which is 4 over here, and x is the message signal. So our message is 0, 1, 2, 3, each 4 bit long, each word 4 bit long. Now we do a scatter plot of w, which will give you the plot, which I'm going to show it to you right now. So as soon as yes, here it is. This one is the scatter plot of 4 bit coin. Okay, fine. Next. Scatter plot of w. We did the scatter plot of w. Now let's see the data. So just to make it clear, 4 is the length, 0, 1, 2, 3. Already told you. Now these are the 4 quadrature modulation. These are the 4 values that came out of the quadrature modulation of x comma m. Now, so the scatter plot that you see over there is a scatter plot of these 4 values. That's it. These 4 imaginary values. So our job ends here. So till this point in the code, you have done the quadrature modulation. But the main purpose of this code is not to do quadrature modulation, but to find the performance, of QAM. So the bit error rate that you need to find, BER, for this one. Now n is equals to 1000. We take 1000 words, 4 bit each. 100 will be the energy. 100 units is the energy of the signal. SNR dB is the thing against which you plot your final figure. So your final figure, which is this one, this axis is SNR dB. As you'll see further in the code, that is what you plot your final BER against. So you have your SNR in dB, 1 to 21 values. Now you create a matrix. In this matrix you have 1, 2 columns and 1, 2, 3, 4 rows. 4 rows and 2 columns. So this is your map, 2 columns and 4 rows. So these actually correspond to the 4 points in the figure, in the scatter plot. Now, I displayed the map over there, so that's fine. Now for 1 to 21, for 21 values of SNR, what we are going to do is we are going to find sigma. So now SNR is in dB. We'll take anti-log of that and we'll convert it into linear scale, which will help us to calculate the sigma. Once we have sigma, I'll just check the time real quick. Okay, so the time is nearly over. So I'll end at this point. Okay, fine. So at this point, I'll end this first part because time's up. You guessed it. Now, so yes, we have the sigma, and further in the code, we'll have to inject the error and we'll have to find the bit error rate.